So if you wanted to eat the absolute most toxic, heavy metal-laced salad on Earth, you'd probably assume, you'd need to forage for it next to some abandoned chemical plant.
Right, or like an industrial waste site.
Exactly. But what if I told you the highest risk of arsenic poisoning is actually hiding in a patch of organic spinach grown in pristine snowmelt, literally 3 miles above sea level in the Himalayas?
It sounds completely contradictory, I know, but that paradox is entirely real. And it's unfolding right now in Ladakh, India.
Which is just a fascinating place.
Oh, it really is. It's this trans-Himalayan region, often called the land of high passes. And I mean, the geography alone is extreme. It sits anywhere from 3,000 to 5,000 meters above sea level.
Wait, that's like up to 16,000 feet, right?
Yeah, exactly. The environmental conditions are just staggering. The defining feature there is hypobaric hypoxia.
Which means dangerously low atmospheric pressure.
Right. It physically deprives your body of oxygen. And on top of that, you have these massive temperature fluctuations. It drops well below freezing at night, but then during the day, because the atmosphere is so incredibly thin, you get hit with this intense ultraviolet radiation.
Plus, it's a cold, arid desert, so there's barely any rainfall, very low humidity, and a really fragile, sandy soil ecosystem.
Yeah. It's an environment that honestly actively resists human survival.
And that actually brings us to the core mission of our deep dive today. Because the challenge isn't just about how humans manage to, breathe or stay warm up there.
No, it's about food.
Exactly. If it's hard enough for humans to just survive at that altitude, what does it take to actually grow the calories you need to live? We are examining how this extreme environment, when you combine it with a shifting climate and human activity, creates a completely invisible food safety crisis for the people living there.
Because when you live in that kind of cold, arid desert, your agricultural window is incredibly tight. There is no year-round farming. The people of Ladakh rely on a single, very short summer cropping season. And because of that, the local population is almost entirely dependent on just a few locally cultivated staples.
We're talking primarily wheat, cabbage, and spinach, right?
Yeah, those are the foundational sources of nutrition for the region.
Which means protecting the safety of those specific crops is just an absolute non-negotiable public health necessity.
Exactly. I mean, if a contaminant infiltrates the wheat or the spinach, there's no backup supply chain they can easily rely on.
And the threat highlighted in the research we're looking at today isn't, it's not a fungus or a swarm of locusts or something.
No, it's heavy metal contamination.
Which is wild.
It is. Heavy metals are these potentially toxic elements that infiltrate the agricultural soil and the irrigation water, like the Indus River, and eventually make their way into the local diet.
Now, I know heavy metal contamination is a growing global concern.
It definitely is.
But I have to push back on this premise right out of the gate. Because when you picture the Himalayas, you picture pristine, untouched mountain air, melting snow.
Right, the classic snow globe image.
Yeah. When we think of human pollution, you think of smog over a massive city. How on earth is enough pollution reaching these remote, high-altitude farms to contaminate entire fields of cabbage?
That's a really good question. And to understand it, you have to look at the physical mechanisms of the landscape. It's this collision of natural geology and the human footprint.
Okay, break that down for me.
Well, first, the Himalayas are young, highly active mountains, and they are naturally rich in elemental ores. So the natural geological weathering is intense.
Meaning the rocks are breaking down.
Right. During the day, water seeps into rock crevices. At night, it freezes and expands, which shatters the rock. And as global temperatures rise and permafrost melts at these accelerated rates, it creates new pathways for water.
So the water washes over these newly crushed rocks.
Exactly. And it leaches ancient, trapped heavy metals directly into the groundwater and the rivers.
Wow. So the warming climate is basically wringing these heavy metals out of the mountain stones.
Yeah, and flushing them straight into the irrigation systems. But then you layer on the anthropogenic footprint.
The human element.
Right. Ladakh is not an untouched snow globe anymore. It has seen a massive surge in regional tourism and development.
Which brings traffic.
Thousands of diesel-powered transport trucks and vehicles winding through those mountain passes. And diesel exhaust, along with brake pad dust, is loaded with heavy metals like lead and cadmium.
Oh, I didn't even think about brake dust.
Yeah, it's a major factor. Those microscopic particles float on the wind, settle onto the snow caps, and then when that snow melts in the spring, all that accumulated toxic dust is carried straight into the fields.
So it's geology plus tourism.
Plus, unregulated waste burning and changes in local irrigation practices, it all hyper-concentrates these metals into this very fragile ecosystem.
Which brings us to the biological mechanism. Because if the soil and the water are full of break dust and leached ores, the plants growing in that dirt become what scientists call bioaccumulators.
Yes, plants are essentially biological sponges, and they are not particularly smart about what they soak up.
What do you mean by that?
Well, their nutrient composition is a direct reflection of what is in the ground. Plants need essential minerals like zinc, iron, and phosphorus to survive, right?
Right.
So their root systems use specific transport proteins to pull these elements from the soil. The problem is that toxic heavy metals often have very similar chemical structures to essential nutrients.
Oh, so they trick the plant.
Exactly. Arsenic, for instance, perfectly mimics phosphorus. The plant's transport proteins just can't tell the difference.
Wow.
So they actively pull toxic heavy metals out of the soil, shuttling them up the stem and locking them right into the leaves and grains.
It is literally turning a healthy vegetable into a Trojan horse.
It really is.
Which leads us to how you actually measure an invisible threat like this. So the researchers behind this study went to Ladakh to quantify exactly what was hiding inside these crops.
Right. And they were hunting for 10 specific elements.
Let's run through them.
Okay, so you have aluminum, iron, cobalt, boron, lead, arsenic, cadmium, selenium, copper, and zinc.
So a mix of essential nutrients and really dangerous toxins.
Exactly. And to get an accurate picture of a region that large, the fieldwork required a really rigorous sampling strategy. They targeted 7 different villages across Ladakh.
Okay.
They collected samples of wheat grains, cabbage heads, and spinach leaves right before harvest. But they used what's called a randomized composite sampling approach.
Now wait, this is where the methodology feels a little, suspect to me.
How so?
Well, the study says they gathered 210 plant samples, which already feels kind of small for an entire Himalayan region.
Yeah.
But then they reduced that down to just 60 composite samples for the actual lab analysis.
Right.
How can they definitively say the food is safe based on 60 mixed up bowls of vegetable dust?
I get why that sounds counterintuitive, but composite sampling is actually designed to eliminate field anomalies. It gives you a much more accurate baseline.
How does mixing them make it more accurate?
Think about it this way. If you test one single cabbage, you might accidentally pick the one cabbage that grew directly over a buried piece of rusted metal, right?
Oh, true.
That single massive spike would skew the data for the whole village. But by taking random samples from completely different corners of a plot and blending them together into one composite sample, you average out those extreme outliers.
Okay, see.
You get a highly reliable snapshot of the overall soil uptake for that entire farm, rather than just the isolated luck of one plant.
Okay, that actually makes total sense. It's like checking the average temperature of a pot of soup by stirring it first, rather than just tasting one weird spoonful from the edge.
That is a perfect analogy, and once they had those representative composites, the lab preparation was pretty brutal.
Yeah, I was reading this part.
The crops were scrubbed with double distilled water, oven dried at 65 degrees Celsius for an entire day to remove literally all moisture. Then they were powdered and sieved to a super fine dust.
And then they subjected that dust to acid digestion.
Yes.
Which sounds intense.
Yeah.
They essentially obliterated the biological structure of the plant using severe chemicals, nitric and perchloric acid.
Right. They heated the mixture until the entire plant matrix completely dissolved. It leaves nothing behind but a suspended liquid of pure elemental metals.
Which is crazy to think about. But that intense destruction is mandatory for the analytical technology they use to measure the metals, right?
Exactly. They use a machine called an inductively coupled plasma optical emission spectrometer, or ICPOES.
ICPOES.
Yeah, it is considered the absolute gold standard for trace element determination in environmental and food safety research.
And I am honestly just fascinated by how this machine actually works. Because it sounds like something out of a sci-fi novel.
The physics behind it are incredible. So the machine takes that acid-digested liquid we talked about, and it sprays it as a fine mist into a plasma flame that's powered by argon gas.
Okay.
This plasma is burning at roughly 10,000 degrees.
Which is hotter than the surface of the sun.
Literally. And at that extreme temperature, the atoms of the heavy metals are physically ripped apart. Their electrons jump to higher energy orbits.
Right.
And when those electrons inevitably fall back down to their normal state, They release a photon, just a tiny flash of light.
And because every element on the periodic table has a unique atomic structure, they each emit a slightly different wavelength or color of light.
Exactly. The machine measures those microscopic flashes of light.
That is wild.
By reading the specific optical emissions, the researchers can pinpoint not just which metals are present, but the exact concentration of those metals down to parts per million.
So it's essentially an atomic level barcode scanner.
That's a great way to put it.
And what's wild is that this hyper-advanced Himalayan research uses the exact same baseline technology that, the FDA uses to test for lead in the baby food sitting on the shelves of your local grocery store.
Yeah, it is the universal standard.
Which brings us to the most complex part of this research, interpreting the data. Because once the ICP-OES spits out a spreadsheet of metal concentrations, you have to translate those raw abstract numbers into actual biological risk for the human body.
Because just knowing there is a tiny amount of cadmium in a cabbage leaf doesn't automatically mean a person is in danger.
Right. We have to figure out how these metals interact with human biology over time. The study uses several internationally accepted health risk models, but rather than getting bogged down in the textbook acronyms, let's break this into two distinct categories that affect the human body.
Okay.
Let's call them everyday toxicity and lifetime risk.
I like that. So everyday toxicity is the baseline. This evaluates the non-carcinogenic health effects.
So not cancer, just general organ stress.
Exactly. And to calculate this, researchers first determine the estimated daily intake, or EDI. They don't just look at the concentration of the metal in the spinach, they calculate the exact dosage entering the bloodstream based on human behavior.
And this is where the math gets intensely personal to the region, right?
Yeah.
Yeah.
They factor in the local diet. So for adults in Ladakh, that averages about 300 grams of vegetables and 400 grams of cereals consumed daily.
Yep.
They also factor in the average adult body weight of the local Ladakhi population, which is about 64 kilograms.
And crucially, they model this exposure over a 67-year average lifespan in this environment.
Right. Because heavy metal poisoning is rarely about eating one acutely toxic meal. It's about the slow, silent accumulation of toxins in your organs over decades.
Makes sense.
Once they have that daily dosage, the EDI, they compare it to a safe reference dose established by global health organizations. This gives us the target hazard quotient, or THQ.
Okay, so THQ is the safety score for a single metal.
Yes. If the THQ is below the safety threshold of 1, your body's natural filtration systems, like your liver and kidneys, can process and excrete that specific metal without adverse health effects.
But the study also calculates the cumulative risk, what they call the hazard index, or HI.
Right. Because a person in Ladakh isn't just eating isolated metals.
They're eating a bowl of wheat with a side of cabbage and spinach.
Exactly. The human body is a single filtration system dealing with multiple contaminants simultaneously.
So it's cumulative.
Right. If you consume safe levels of lead and safe levels of cadmium and safe levels of aluminum all in the same meal, those metals can synergize. The combined stress on your cellular pathways can overwhelm your system, even if no single metal crossed the danger line on its own.
So if THQ is like having one cup of coffee and your fine HI is looking at what happens when you have a coffee, an energy drink, and a soda all in the same day.
Yes.
One caffeine source might not cross the line, but all of them together might make your heart race.
Exactly. The hazard index sums all those individual risks to ensure the cumulative burden remains below that threshold of 1.
Okay, so everyday toxicity is evaluating whether your organs are being overwhelmed today, tomorrow, or next year. But then we have to talk about the darker side of the data, lifetime risk.
Right. Lifetime risk focuses specifically on carcinogenic risk, or CR.
And the target cancer risk, TCR.
Yes. Some of the metals detected most notably, arsenic, cadmium, and lead, are known carcinogens. They don't just stress your organs, they actively damage your DNA at a cellular level, which causes mutations that can lead to cancer.
And the threshold for what is considered an unacceptable cancer risk is incredibly strict here.
Very strict. Environmental toxicology uses a metric called an oral cancer slope factor. The unacceptable risk level is defined as anything crossing 1 × 10⁻⁴.
Which translates to a greater than 1 in 10,000 chance of a person developing cancer purely from consuming these local crops over a 67-year lifespan.
Yes.
To put that in perspective for you listening, if everyday toxicity is like getting a sunburn, it's damaging, but your body heals. Lifetime risk is like being forced to buy a micro ticket for a cancer lottery every single time you sit down for dinner.
That's a grim way to put it, but accurate.
You want your chances of holding the winning ticket to be as close to zero as structurally possible.
And the tension in the study really peaks right here. I mean, you have an incredibly harsh environment where people rely entirely on their local harvest. You have mountains releasing ancient ores and tourist vehicles dumping brake dust.
You have plants that actively absorb these elements.
Then you have atomic level safety thresholds.
Drum roll. What did the data actually reveal? Are the people of Ladakh slowly poisoning themselves just to survive?
Well, the immediate headline is highly reassuring.
Okay.
When the researchers ran the numbers for everyday toxicity, the cumulative non-carcinogenic risk, that hazard index for all the crops, fell well below the threshold of 1.
Oh, that is a massive relief.
It is. The daily diet in Ladakh is not currently overwhelming the local population's baseline organic function.
The wheat and the cabbage, which make up the bulk of the caloric intake, are holding the line.
Yes. But, and this is but that relief comes with a massive biological caveat, because these plants do not behave the same way in the soil.
What do you mean?
They behave radically differently. The sequence of metal absorption generally prioritizes iron, followed by aluminum, boron, zinc, and copper. But the most vital discovery was which plant was pulling the heaviest load. The data showed that spinach possessed a significantly higher mineral and heavy metal content across the board compared to both wheat and cabbage.
Wait, really? Spinach?
Yeah.
I mean, we are culturally conditioned to view spinach as the ultimate healthy superfood.
I know, it comes down to the architecture of the plant itself.
How so?
Spinach has these broad, expansive leaves and a very high transpiration rate. As water evaporates from those large leaves into the dry mountain air, it creates this powerful upward suction in the plant's vascular system.
Like a straw.
Exactly. It pulls large volumes of water from its deep taproots. And because spinach is so highly efficient at pulling up groundwater to survive the arid climate, it acts as a hyper-efficient vacuum for anything dissolved in that water.
Including heavy metals.
Exactly.
Which leads directly to the singular glaring red flag in this entire study, the lifetime risk.
Yes. While the cancer risk for wheat and cabbage remained just below the danger zone, the target cancer risk value for spinach specifically crossed the unacceptable risk threshold.
Wow. So Popeye's superfood, the leafy green that provides essential vitamins in a region devoid of fresh fruit, is actually handing out those winning cancer lottery tickets.
In this specific contaminated high-altitude environment, yes, it is.
And it's just, wow.
And the danger wasn't an even spread across all 10 metals either. There was a specific culprit driving the toxicity.
Let me guess.
Arsenic. Arsenic was the overwhelming driver of the biological danger. When researchers calculated the total cumulative hazard, arsenic alone accounted for 77% of the risk in wheat, 75% in cabbage, and a staggering 80% of the hazard risk in spinach.
80%? So arsenic, this element naturally present in the Earth's crust but heavily disturbed by human activity, is masquerading as a nutrient.
Mimicking phosphorus, right?
Being sucked up by the most aggressively thirsty plant in the garden and quietly damaging the DNA of the people eating it.
It highlights a really tragic irony. In an environment where simply cultivating enough food is a monumental achievement, the biological resilience that allows spinach to thrive in the desert is the exact same mechanism that makes it toxic.
Yeah. And as we zoom out, the implications of this research stretch far beyond the borders of Ladakh.
They absolutely do.
Because if you are listening to this right now in a sea-level city thousands of miles from the Himalayas, you might wonder why the heavy metal content of a distant mountain farm matters to you.
It matters because it proved that the concept of a pristine, isolated ecosystem no longer exists.
Anywhere.
Right. Ladakh is one of the most remote, untouched-looking environments on the map. Yet the combination of shifting global climate patterns, melting permafrost, and the creeping footprint of tourism has fundamentally altered the chemistry of their soil.
The baseline of global food safety is quietly moving beneath our feet.
The soil remembers everything. The climate shifts, the diesel exhaust, the industrial dust, and it passes that memory directly into the food chain.
And the researchers make it clear that while the non-carcinogenic levels are safe right now, the rapid urbanization and increasing tourist load mean the carcinogenic risk is only going to climb.
It will. We are watching the slow-motion pollution of the world's most extreme agricultural outposts.
Because the mechanisms of bioaccumulation don't stop just because a region is remote.
Exactly. Plants will keep acting like sponges.
Which actually leaves me with a final, slightly provocative thought to carry away from this.
Okay, let's hear it.
We have just spent all this time detailing how incredibly efficient plants like spinach are at vacuuming heavy metals out of contaminated dirt, right?
Yeah.
They are so good at pulling up arsenic and lead that they become dangerous to human biology.
Yeah.
So, if we know these plants act as biological sponges, could we weaponize that mechanism?
Oh, I see where you're going.
Could we intentionally plant massive fields of specific sponge crops in highly polluted industrial areas, not with the intention of ever eating them, but solely to clean the earth?
Like harvesting the pollution.
Exactly. Could we literally sacrifice an entire harvest, letting the plants suck up decades of lead and arsenic, and then safely dispose of them just to heal the soil for the next generation of crops?
It is the ultimate pivot, taking the biology that creates the crisis and using it to engineer the solution, bioremediation on a global scale.
Right. It is definitely something to ponder the next time you see a resilient little plant pushing its way out of the dirt. Thank you for joining us on this deep dive. Keep questioning the invisible forces around you, look closely at the science hidden in your everyday life, and remember that no matter how high up you go, we are all ultimately tethered to the soil.